Well, welcome to another episode of Let's Talk Creation with Paul Garner and Todd Wood. I'm Paul Garner.
And I'm Todd Wood.
If you're enjoying the podcast, please consider helping us out by liking and sharing our episodes, subscribing, hit that notification bell, tell your friends about us. All of that really, really helps us to grow our audience. And it's great to see new people joining us every couple of weeks when we launch a new episode. That's really great to see. But we'd love to have more of you on board. So come and subscribe. It's free. Doesn't cost anything. Now, in this episode, we are going to be thinking about transitional fossils. It seems as though all sides in the origins debate talk about transitional forms, kind of obsessed with it, really. So what do we mean by transitional forms, Todd? What do we mean by that term?
It's kind of a loaded term, isn't it? Right?
It is.
So usually when you think about, think about creatures, you can think about large groups of creatures, say, like mammals, right? So mammals are this big, diverse group. Aardvarks are mammals, and elephants are mammals, and monkeys are mammals. Your cat is a mammal. They all have, fuzziness and give live birth. That's the kind of thing. They make milk. Those are the kinds of things that puts mammals together. And then you have other groups of vertebrates. Let's make up one. Let's call it reptiles. Now, I know there's a lot of diversity within what we think of as reptiles, but reptiles, classically speaking, the way our audience would probably understand it, they're scaly, they're cold-blooded, they lay eggs. Those are sort of reptilian characteristics. And then a transitional thing would be a thing that has characteristics of both of the big groups, right? And so a platypus might be a transitional thing. It's furry like a mammal, but it lays eggs like a reptile. So it has characteristics of both groups. Now, the evolutionists would say this is evidence of evolution. This is how things evolved over millions of years. Creationists traditionally have chosen to simply deny that any such things exist. That transitional forms are nothing of the sort. And so, and those, to our credit, we do want to emphasize there's other ways of thinking about them. We could call them intermediates, right? We could simply say that they're sort of, or they're mosaics, right? They share characteristics. They're not transitional in the sense of actually making a transition between one thing and another. But anyway.
And from an evolutionary perspective, these kinds of morphologically intermediate things are particularly impressive when they're in a stratigraphically intermediate position as well. So they're in the kind of right place in the rock layers to be between the ancestral and descendant groups. So so everybody's obsessed with transitional forms. The people on the evolution side kind of see this as, here's the slam dunk argument for evolution, right? So, this kind of proves evolution. And like you say, creationists spend a huge amount of time writing about transitional forms, mostly to try and say they're not really transitional at all. Now, in previous episodes, we've spent quite a bit of time thinking about transitional forms. But I think what we've tried to do is bring a different perspective. So a perspective that's kind of free from a lot of the polemics. Our goal has really been to try to understand, how we interpret these fossil organisms from a creationist perspective, rather than just kind of hurling rocks at, across the divide, right? So in episode 8, we did an episode called Where's My Missing Link? Where we kind of introduced this whole sort of concept of transitional forms. And if you want that sort of introduction, go back to that. That was really early in our podcast series. And we just sort of talked generally about how we might understand transitional forms within the creation model. And then in episode 42, we looked at a specific example. We looked at the horse series, the famous horse series, where, you have the little horse, Hyracotherium, with, it's quite small and it's got browsing teeth and it's got multiple toes. And Yeah, and then through the fossil record, we kind of see this huge diversity of horses, and then you've got the modern horse, the horse that we're all familiar with the single hoof and the grazing teeth. And we took a look at that. We talked to Tim Brophy, didn't we, about the horse series. And of course, we've devoted quite a number of episodes to the ape human transition, where we've been looking at fossil hominins, because that's a particular research interest, Todd, of yours. So we've devoted, I think, at least 5 episodes to fossil hominins. But
Something
yeah,
like that,
so
yes. You could say I'm
something like that.
obsessed even, something
You
like
you
that,
could
yeah. Yeah.
you could. But there is one series of transitional forms, transitional fossils, and I do mean a whole series. So we're not talking here about just an isolated fossil or two that we haven't really looked at yet, and uh, that is the series known colloquially as mammal-like reptiles. I'm sure our guest is going to tell us why um, he doesn't like that term, mammal-like reptiles. But anyway, in evolutionary terms, the mammal-like reptiles are kind of the fossils that span the reptile to mammal transition in the fossil record. So that's going to be the focus of today's episode. And it
Yeah.
turns out that some really interesting creationist research on the fossil organisms in this series is currently being done. And so we thought it would be fun to talk about that in this episode. And to help us, we have a returning guest to the podcast, Dr. Matt McLain. Matt, welcome again to the show.
Hey, thanks for having me again.
It's really great to have you. Now, for those who've regular viewers, listeners, they'll know Matt. He is a professor at the Masters University. You're a paleontologist, Matt. I'm sure you can tell viewers anything else you think they need to know about you. But why don't we sort of launch into this topic? Because I know you've done some really interesting research in this area. I think in past episodes we've talked to you about dinosaurs, and that's something else you've sort of thought about. But this is something else that you and your students have sort of worked on. So why don't we start at the beginning? What kind of got you into this particular area of research? Why study the mammal-like reptiles? And is that a good name for them?
So, it's all dinosaurs. Dinosaurs, that, even, I guess in the new Jurassic World movie, they were saying mosasaurs are dinosaurs. Everybody's a dinosaur, right?
Right.
But there's so much more out there besides just dinosaurs. And that's unfortunate that they steal all of the spotlight because there's so many fascinating creatures that God made. And when I first started learning about these creatures and realizing, oh, these aren't dinosaurs, what are these things? And realizing everyone's like, what they know, they're really weird. And so it got me really interested in them. And so actually one of my absolute favorite animal is is one of these creatures, one of these mammal-like reptiles. And that's a Steminasuchus. I'll show you right here. I got one. Look at
Oh,
look at
wow.
this guy. What a wild creature, right? And he can even, open his mouth. Okay. So for those of you who are listening, I'm showing them a little toy of this guy.
Yeah.
And
He
so
looks
he
like he's
basically, Todd,
got
how would you describe this creature?
he looks like he's got his hair done up in little hair ties. He's got little short hair and he's got little tiny little pigtails sticking on top of his head there. And big floppy
Yeah.
ears on the side of his head. Is that what I'm looking at there?
So it's not hair and not ears. That's all
Not
bone.
hair, not ears. Okay.
So these
No.
they're like bony antlers almost. Except they don't shed them as far as I can tell. And then there's bony projections coming off either side, and it's actually got a little horn on his nose, just because he wasn't weird enough already, and it's got fangs, and then it's basically the size of a small hippo. So you could ride this if you wanted to, which is pretty cool to think about.
Wow.
Um,
Crazy.
and so it's like, what is this? Right? What do you call this thing? I mean, is this a reptile? Is it a mammal? It's clearly a vertebrate, right? It's got bones. It's clearly a tetrapod. It's walking around 4 legs. But it's really, really unusual. And so when the first fossils came out, that was the late 1800s. So Richard Owen described one of the very first ones. It came out of South Africa. He got wind of it, and it was from a dicynodont, which I will show you one of those. I've got a model of one here. Looks like a potato. You can see. But they have a beak and they
What?
have tusks. Okay, now this one, these aren't actually. This is a bad example. These aren't actually tusks. They're bone pretending to be tusks, which is really weird.
Wait,
Normal ones
what?
actually have tusks. So hold on, I've got a normal one for you. Okay, I've got a normal one now. Okay, so this guy, this is a skull from one, and so it has a beak like a bird, like a
Uh-huh.
turtle or an eagle or something, and then it's got these two tusks, kind of like a walrus. And then you can see the whole animal's kind of pig shaped. And the first one of these, Richard Owen was describing, he said, it's some kind of reptile. It's a really weird reptile we don't have today, and it's got a beak like a turtle. And then he took really, really close, he paid really, really close attention to the teeth, the two tusks. And he realized these look like mammal teeth. And that really threw him off, because it didn't really fit either classification. And so you can see Richard Owen trying to think through this, because this is pre-Darwin, Darwin's, Origin of Species. And he's thinking about, what could this mean? Actually, hold on, sorry, I might have to cut this. It might be after Origin of Species.
No.
Richard Owen is not
Richard Owen
a
wasn't a
friend of
big fan of
Darwin.
Origin of Species anyway, so he's
It
definitely
doesn't
gonna
matter
be.
either way. So
Yeah,
let me
yeah.
say this instead. So Richard Owen's not thinking about evolution about this, but he's trying to make sense of this, right? And so he's like, well, it's a creature that has some features of a reptile and some features of a mammal. And so, of course, evolutionists latched onto that as they found more and more fossils, and they said, hey, we've got an actual transitional sequence here from the origin of mammals. So, you had people like Huxley who was saying maybe mammals came from amphibians. But with these creatures, everyone's like, no, we got it. They come from reptiles. But the problem is they're not reptiles. Okay, so that's why the mammal-like reptile name is bad name. And so that was used back in the day. Nowadays, we don't say that. We instead refer to this whole group as synapsids. Okay, so that is because of the skull. Okay, so I've got a dinosaur skull here. It's very colorful, you can
Nice.
see. And it has the eye hole here, and it's got the nose hole right there, right? And then it's got a hole here and a hole there. Okay. And so these are called the temporal fenestrae. That's the fancy term. We're just going to call them the holes. Okay. So it has two holes, got two holes on each side. Okay. These guys only have one hole on each side. So this is the skull of
Oh.
Dimetrodon. This is life size because it's a replica. That's this guy, the guy with the fin on his back. Okay,
Yeah.
so when you were a little kid and you got your little
Yes.
dinosaur
I got
toys
a
in a
bag of
bag, this is one that
dinosaurs.
would commonly show up. Yeah,
Yeah.
Yes.
he is not a dinosaur.
No.
Okay,
Ah.
and the reason, one of the ways you can easily tell is that he does not have the dinosaur skull construction. So he's got the nose hole, he's got the eye hole, but he only has one hole back here. There's nothing else going on there, right? And so synapsids only have one hole. And mammals, when you do like cladistics and all the modern classification system and everything, they placed mammals in this group too. We also only have one hole back here. You might say, I don't feel like I have any holes. Okay. Well, if you look at a human skull, we've got a little human skull here, not a real one. You got your nose hole, you got your eye holes, and then you've got this space right here, right? And that is the temporal area, right? So when you put your hands on either side of your head, right? Like you've got a headache or something, and you start biting, right? You will feel, this is great to watch you guys do this. You will feel muscle moving there, right?
Yeah.
And that's because that temporal fenestra, that area there, that is typically for muscle attachment for the jaw muscle, right? So the jaw muscles run down from the skull, they go through there down to the jaw. And so that's what's allowing you to open and close your mouth. So these animals are not reptiles, which will have other arrangements in the skull. They're their own group, the synapsids. And then modern classification, they put mammals inside synapsida. So they would say there's
Right.
mammals, and then there's other synapsids, which are these fun guys, right? All these dead guys. And so we can talk about their names when we're ready, so we don't totally go jargon heavy really fast.
So Dimetrodon is
Yeah.
not a dinosaur.
He is not.
Yet another example where a dinosaur guy tells you, "Oh no, that's that thing in your bag of toys. That is not. You got your bag of plastic dinosaurs, which many of us did as kids. Contain many things that are not dinosaurs." Yeah.
Lies.
Yeah. Yeah.
Sad.
Yeah, but paleontologists are here for more than just bursting our bubble. So, yeah. So let's so let's think about these things. So that you've got these things called synapsids, and like you say, cladistically, mammals kind of fall within that broader group. But there are other things that are non-mammalian synapsids, we might say, and I guess that's what in the old term we used to call mammal-like reptiles. So why did you get particularly interested in these animals? I mean, apart from the fact that they're just kind of fascinating and weird, and they're intrinsically interesting. Why, as a creationist, are you looking at these guys?
So I remember in college, I picked up a copy of T.S. Kemp's, I think it's called On the Origin of Mammals and Mammal-Like Reptiles or something like that. And from 1982, it's a fantastic book. Took forever reading it. Had a roommate who was like, "You're still reading that? But return it to the library." And I just found it really interesting. And I realized as I was reading, of course, hey, this is something creationists need to address, because you've got this sequence of animals that, as you said, they look morphologically intermediate, right? They look like you're turning a reptile into a mammal. And then they also work with the stratigraphy. So the more reptile ones are lower, and the more mammal-like ones are higher up in the rock record, right? So they're more recent. And so I was wondering about, okay, what do you do with these things, right? So I was very curious about them as a creationist for a long time, and kind of dabble and looking in things. When I became a professor later, and here in the Master's University, and I was teaching my first vertebrate paleontology class as a lab for the students in there, I would have them do a baraminology lab. It was one of the labs they do, where they would learn how to do a baraminological analysis, statistical baraminological analysis, and they could pick any group they wanted. And so one of the students was like, it was Abigail. She was Talavera Castanoli at that point, but she said, I really want to look at these mammal-like reptile creatures, these non-mammalian synapsids, because I find them really interesting. Like, oh, great, I do too. Let's do it. And so she worked on one particular group, I worked on the rest of them, and then we started figuring out, okay, what does this look like? And we started doing this research, and then that was just the first step, and then it was just fallen after that, right? So then I had other students helping me, and then I did my own stuff, and eventually this last year I had a semester off doing a sabbatical, doing research on these things, trying to really get a strong, good handle as a creationist on this topic. Because you pointed it out, right? We talk about dinosaurs. You guys have done multiple videos on hominids, right? You even talked about horses. You haven't talked about these. And that, if you look at the creationist literature, that's exactly what it is. There's only a few times that creationists have even mentioned these, and even fewer times that someone has actually, tried to answer any of these questions.
Yeah.
In our defense, I think it's a branding problem, to be honest with you. So
We need a cooler name.
other transitional groups have great names, right? You've got
That's
your
true.
feathered
Right.
dinosaurs, you've got
Yeah.
you got your archaeocetes, ancient whales, you got your
Walking
hominins,
whales.
like
Yeah.
humans, and then you've got your non-mammalian synapsids. What even is that? How do I even explain that? How do I get anybody excited about that? I don't know.
Yeah.
You gotta show 'em
got to work on a
pictures.
better name for their
I
group,
know.
Yeah. So when you were saying you kind of got going on this baraminology analysis, you're talking there about basically trying to identify created kind. So we've talked about that in past episodes. And you can use some statistical sort of analyses to sort of start to figure out, what belongs to which kind. So we'll come back to that. So I kind of want to dig down a little bit into this whole issue of reptiles and mammals at this point. So the reason, that people get so excited often about these non-mammalian synapsids, these mammal-like reptiles, is that they are thought to be the classic sort of evolutionary transitional series. They've been called the crown jewel of evolution, right? So this is the textbook example. So let's think about the major differences then between reptiles and mammals, because if these creatures are meant to be evolutionarily transitional between the two, when we look at modern reptiles and mammals, we can see some obvious differences, right? So talk to us about what the differences are that we see at least in the modern world, when we look at
Yeah.
reptiles and mammals.
Yeah, so Todd already brought most of those out, right? Most your mammals give birth to live young. You got a few exceptions. Modern reptiles lay eggs. Once again, there's exceptions. There's some snakes that give birth to live young and stuff. Modern reptiles have scales. Modern mammals have fur. And then there's the whole milk thing, endothermy
Mhm.
versus exothermic, right? So warm-blooded, cold-blooded. Although that's
Mhm.
really challenging because you've got leatherback sea turtles that are basically warm-blooded, and you've got mammals that act as if they're cold-blooded sometimes. So it's a whole mess. But
Yeah.
there's clear differences, right? I don't walk up to a creature and like, is that a reptile or is that a mammal? Like the
Mhm.
only time that happens is if I'm looking at like a pangolin or an armadillo or something. For a minute I'm like, and they're, oh yeah, I can see
Mhm.
the fur. But that gets more complicated when you look at extinct creatures, right? And that's because we named our groups off of the creatures we knew about, right? We didn't know about all these creatures when we started doing taxonomy. And so you've got really crazy stuff in the fossil record for reptiles, right? Where you've got reptiles that look like whales or dolphins and that give birth to live young. You've got reptiles that, could fly, right? And they are probably warm-blooded and had little fuzzy covering all over them. Talk about pterodactyls and stuff like that. And then you had these guys. And so, and
Yeah.
plus the problem is most of the things we just talked about don't leave good fossil evidence, right?
Mm.
Milk doesn't fossilize well. I mean,
Mhm.
it expires in like no time at all, right? It's frustrating like that. And you've got fur typically doesn't leave good fossils. And you very rarely are going to fossilize something giving birth to live young. I mentioned ichthyosaurs, these dolphin-like reptiles that we do see evidence of them giving birth to live young, but it's rare to find that, right? So you want to look for skeletal features. And so one of the clear ones with mammals that's very easy to see, and I've got a human here. Modern, evolutionists consider humans to be, hominid primates. We talked about this in earlier episodes and stuff. And regardless, we follow the same pattern skeletally for a mammal, right? And so one of the things you'll notice is that the lower jaw is all one bone. So this is the bone we call the dentary.
Yep.
Although the human anatomists call it dentary, they just call it the mandible. What do they do? I don't even know.
It's called a mandible
I
usually,
don't.
but
Yeah.
Yeah, they
you
always
could call
change
it a
the
dentary.
rules. It's so frustrating. Every
Yeah, I
animal,
know.
oh, it's a zygapophysis. You get to a human. No,
But
it's
it's constantly happening. I mean, we're constantly revising. I mean, don't even get me started about the two groups of dinosaurs. So, but anyway,
So we got one bone, right? It's
Yeah.
just this dentary bone right here. And when you look at a reptile skull, so I'll use our dinosaur over here as a nice example because these are all color coded. The real animal obviously is not color coded, but you can see the blue here. That's the dentary where the teeth are, right? But
Yeah.
there's all these other colors. You can even see
Mm.
some more on the inside. And that's because reptiles have lots of bones in their mandibles. Okay, so they've got the dentary, but they've got a syringular and an angular and articular and a splenial and all these funny bone names. Okay, and so that's one very obvious difference between us and the mammals versus reptiles. Okay, another one is our ears. So
Mm.
in a mammal and in humans, we have these tiny, tiny bones hidden in our ears. Okay, and they are called the incus, the malleus, and the stapes, or people call them the hammer, anvil, stirrup. And I did those in the wrong order, but and they're tiny, right? They're these little intricate, super tiny bones. You can fit the human ones on a coin, right, on a penny. And they are very intricately designed to help us hear. And it's a really cool design. I don't know if you guys have done an episode on the human ear or anything like that, but that's a classic creationist discussion, right? You
Mhm.
hear creationists talk about that all the time, how well designed our hearing is, and it is. Reptiles aren't like that. So reptiles just have one bone that goes back in here, and it's called the stapes, and it's just this long rod for the most part. And you have a cartilaginous extension on it. And so
Mhm.
reptiles typically don't have as good of hearing as a mammal. We tend to have much better. We can hear wider range of frequencies and all kinds of cool stuff like that. And so the other big one that you can tell from skeleton also, and I don't know how many bones for this, but I don't need to show you. You can figure this out. Mammals walk with our legs directly beneath their bodies. Okay, so an elephant, you watch it walk around. Dogs, versus I have a lizard for a pet. Our bearded dragon, Lemony Snicket. He's got his legs way out here, and so he walks really funny, right? And so He will sometimes drag his belly as he walks. It's this sprawling posture, and he can only like run for little bursts, and then he's like, oh, and then he gets what's going again. And it turns out the reason, part of the reason is because as a lizard runs, its spine goes laterally like this, like a fish, right? Or a snake. And what's actually happening as it moves side to side, it has to collapse that lung as it moves side to side.
Wow.
And so they can't like run for really long distances because they're going to be out of breath. Versus a mammal, our spine goes up and down as we run for the most part. And so that allows for us to have this like longer period, this endurance that we can have during running, which is pretty cool. And so it's just different design and different creatures, but you can tell them apart.
Yeah. Yeah, well, I mean, speak for yourself on being able to run a long way.
Yeah.
Without running out of breath.
Yeah.
Anyway, I don't know what that says
He's a
about
lot
me.
younger than we are, Paul. That's what's going on here. Young kids in
so-
there running.
Exactly. So in the modern world, we've got these fairly obvious sort of differences, and between reptiles and mammals. You got some oddities, as you say, but there are some basic distinctions. But when we get back to the fossil record, it kind of starts to get a bit fuzzier, a bit blurrier. So just help us sort of understand that. What kinds of things do we see in the fossil record that kind of make us scratch our head and think, well, is this a mammal? Is this a reptile?
Yeah, it starts getting kind of interesting, right? So the skull's the easiest one. So, I will show you. I'm going to show you one. Hold on 1 second. So, I'm going to show you a little guy here. This is a non-mammalian synapsid. His name is Olivier-Asuchus. This is a
His
skull,
name is
little
what?
tiny guy.
What is his-
Olivier-Asuchus.
Okay.
Yeah. So he's a therocephalian, which means beast head. Okay. Or beast skull. And what's interesting about this creature, so it's got different types of teeth in its mouth. First thing you notice, it's actually got incisors in the front, it's got a canine right here, and it's got post canines. And they're different in shape, right? And we didn't mention it, but that's a very mammal trait, right? Having, you go to the dentist and they tell you, oh, your canine, you got a cavity on your premolar or something like that, right? You got these different types of teeth in your mouth. Whereas most of your reptiles, pretty much the whole mouth is just one type of tooth. Sometimes you have little shape differences and things, but that's rare. But then also, the lower jaw, so the dentary here, goes all the way back here. And then all these little bones back here are those extra bones. So it's not like the dinosaur I showed you earlier, where like the dentary is only this part, and then you got a big bone there and a big bone there and everything. It's like the dentary makes up most of that, and you got these little bones. And so it's like, well, that's weird. It's almost looking like a mammal jaw, except there's just this extra stuff jammed in the back here, right? And what's really interesting about a lot of these guys is that in this group and a couple of the other groups, you will actually see what's called a bony secondary palate. And so in mammals, there is bone that goes up on the palate, and that allows for the air coming in your nose to be separate from the air coming in your mouth. Okay. And they meet towards the back. Reptiles, for the most part, don't have this. The air just meets immediately. And so there's a lot of advantages. The bony secondary palate, right? It helps if you think about baby suckling. But it also just helps in general. Like I can breathe through my nose while I'm chewing on something, right? My lizard can't do that. He'll chew for a little bit and he's like, he start chewing because he's got to take that breath. So, but crocodiles, oddly enough, do have a bony secondary palate. But some of these non-mammalian synapsids, you can see these mammal-like traits popping up. And it'll be the same bones in some of these guys. So like our cynodonts, which are one of the groups there, they will have this bony secondary palate right here that is made up of the exact same bones as in a mammal. And they'll have the different types of teeth in their mouth. And you can see in this guy, basically the whole lower jaw is the dentary. All of the extra bones are crammed on the inside, like these thin rods right here.
Wow.
And one of the things we didn't mention, but that's really important in this transition, is the jaw joint, right? So in a mammal, our jaw joint is, and this is true in humans as well, the jaw joint is between the dentary, or the mandible, and the squamosal, or the temporal, I think they call it in humans. And so reptiles have a completely different jaw joint. They have between a bone called the quadrate and another bone called the articular, okay? And so It's like that's a big difference. Well, you've got animals that have really, really tiny quadrates and articulars, and they're really, really close to the dentary and squamosal, and it looks like they may have actually had double jaw joints, had both at the same time. And so for an evolutionist, you're starting with non-mammalian synapsids that look more like reptiles, like this guy, Dimetrodon, right? And so he's called a pelycosaur. That's the more primitive, more reptile-like ones. And then you move into these other guys we call the therapsids, which are the ones that look more mammal-like. And then finally, you would get to your really, really mammal-like ones that they call the cynodonts. And so that's kind of the story that they imagine happening there. You see the posture become more mammal-like. You see the jaws become more mammal-like, all that kind of fun stuff. And so there's this transition that they believe has happened there.
Hmm. Well, I mean, now you've got me really worried because the way you've kind of described it there, I mean, that sounds like a really good argument for evolution, right? And
I'm
this is
convinced.
why, yeah, I mean, this is why people point to this series of fossils and they say, here's the slam dunk, for evolution. Yeah, it's really interesting that you kind of see what looks like increasing mammal likeness as you kind of go up through the fossil record. And talk us through, how should we respond to this as creationists? And maybe there are some general kind of lessons, principles that we can sort of draw out when, as creationists, we're confronted with some evidence or an argument that seems like a really good argument against our position. What should our response be? What are the different ways we could respond? What are the advantages and disadvantages?
Yeah. So let me do that by giving their absolute best evidence, and then we talk about kind
Sure.
of how we respond to that.
Yeah, sure.
So I mentioned the jaw joint, I mentioned the ear bones,
Yeah.
right? So how do you actually make that transition? Because that sounds crazy. What, I'm supposed to switch bones to make a jaw? That's absurd, right? Oh, I'm supposed to grow ear bones? Like, where do those come from? How is this going to happen, right? And I'll tell you what they say first, and you're going to think that's
Okay.
ridiculous. That's silly. There's no way. They say those extra lower jaw bones turn into ear bones. Okay. And that sounds
Okay.
like nonsense, right? Like, no, what would a transitional state look like? Like, how could you have you have like some bones halfway in your jaw? Somehow it's weird. But when you actually look at their evidence, walk through their evidence really briefly, and then we'll kind of talk about what do you do with that. So, in an animal like this little cynodont, Probetonathus, I mentioned, all those extra little bones are crammed right here, right?
Mm.
And you're getting close to what looks like two jaw joints, okay, is what their claim is. And then in an animal that many people call a mammal, called Morganucodon, this little Triassic, little shrew-like thing, you can actually see both jaw joints are there. It clearly has, I would argue, a double jaw joint. But those little those little jaw bones, those extra little jaw bones, they make a little ring, okay,
Mm.
and on the lower jaw. And it turns out if you look at some other of your mammals that you find in the Mesozoic, so Triassic and Jurassic mammals, they look like those bones are their ear bones, and that ring surrounds the eardrum, okay?
Mm.
And they are actually attached to the lower jaw. And there's one animal, Eunoconodon, where you can actually see they're like branching away from the jaw, and they're preserved that way. Like they were actually attached to the lower jaw, the ear bones. And you think, that's so weird. But if you look at a mammal, so like a pig, and you watch its embryonic development, it turns out that we have 3 ear bones, right? 2 of those ear bones begin from jaw material. So the same tissue that our jaw grows from, 2 of the ear bones grow from that. And then they detach from that and they become part of the ear.
Hmm.
And that was discovered before Origin of Species, before everyone was obsessed with evolution by natural selection. That was just a German anatomist looking at pig embryos, right? And so you can quickly see how an evolutionist is like, there you go, right? You've got reptilian jaw, you've got these jaw bones, they shrink, they go to the back of the jaw, they make these ear structures, they break away from the jaw, they turn into our modern ear bones in a mammal, and it's recapitulated in our development, right? We can
Yep.
see that story happen again in embryonic development. And
Yeah.
so that sounds like a really powerful story, right?
Sure.
And
And
you've got, oh, go ahead.
now you've made the whole problem even bigger.
Yeah, even worse.
Yeah,
Thanks
just
a
trying to
lot,
worry you as
Matt.
much as I can. That's my plan.
Yeah.
Yeah. Did the
So
exact opposite of what you wanted. Yeah.
yeah, so I mean, how do we respond to this as creationists? You know,
Yeah.
what do our audience members make of this?
So, let's talk about what you don't do, right?
Sure.
What you don't do, number one, is give up. I have met people who have encountered some particular argument in favor of evolution or against creation, and they're like, "That's it. I'm done. Like, I don't know how to answer that. So evolution's right, Bible's wrong." And more often than not, you wait 10 years, 20 years, and somebody's like, everything we thought about that was wrong. Turns out it's something different. And I think about Paul in particular when you talk about granite formation. I think you
Mhm.
did a really good talk on that, where you're like, yeah, when I was a student, this seemed overwhelming.
Yeah.
I mean, it seems so clear that granite had to cool really, really, really slowly. And nowadays they're like, nah, you can make granite like there's nothing.
Yeah.
What? What? And so you think, man, you abandoned something of eternal value simply because you didn't have an answer to a question at the moment. I mean, that's
Mhm.
that's that's not a good trade, right? And
Mhm.
so framing it in your mind that way, hey, is this worth trading this for? And I don't think it is, right? When you talk about scripture and the truths that God has revealed to us, those have eternal value. Those are good things. So we hold on to that. That's number one. We don't let go of that.
Yeah.
I think number two, what we don't do is we don't deny that there's a problem. And this is a trap
Mhm.
sometimes we as creationists fall into, is we kind of belittle it or
Uh-huh.
pretend like it's not a problem. Oh, those evolutionists, they find one bone and they just make up the animal, right? Or, oh, those evolutionists, they don't have any actual, I mean, Todd knows this all the time with the hominids, right? People are like, oh, there's no evidence for a missing link with humans. No one's ever found anything that looks good. They're all just fake. Those are not good approaches, right? You're not actually dealing with the data.
Mhm.
Um, and then I think the third trap we fall into is we get too attached to our assumptions and our schemes and diagrams and things. So we talked about what is a reptile, what is a mammal. Really obsessed with those terms. And we forget that, okay, those are words we made up to describe something we see in nature.
Sure.
We should be willing to let nature kind of determine how we think about it, right? It's the same thing with your text of scripture, right? You don't come to scripture with, well, I want to say these things. I'm going to make it say these things. No, you try and draw out of the text what's there, right? And same thing with nature. We don't want to come at it and say, well, there's only two groups and it's got to fit in these two groups and you just shoehorn it in there. No, you've got to make sure that your groups actually reflect what you see in nature.
Sure. Sure.
So last thing I think we shouldn't do is it goes with the deny one, but deny similarity. And this is a trap that creationists often fall into. I was just talking with Ken Colson the other day about this, that we sometimes, because we know there is discontinuity in history, right?
Mm.
That there's not this evolutionary tree of life. God actually made different kinds of creatures. Like that's very clear from Genesis. They have separate origins sometimes on different days, right?
Yeah.
And we also deny that random chance and mutations and time can create the diversity of life, right?
Mhm.
No, like we genuinely think that there's design at work here. And that's, once again, that's biblical to think that. What we end up starting to do is we kind of are uncomfortable with any talk of continuity, any talk of
Mhm.
things being similar to each other. I mean, I'll run into people that I'm like, well, yeah, like I think a tiger and a lion share a common ancestry. If there's one type of cat that got off the ark, and they're like, whoa, talking like I'm like, have you ever seen a tiger like and a lion? Like they're the same animal. I mean, it's just they're just wearing different clothes. Like if you look at their skeleton, you basically can't tell them apart. And so, but more than that, like, I should be perfectly comfortable saying a human has more in common with a dog than it does with a fish. Like, that's not an evolutionary statement. That's just general observation, right?
Yes.
Like, fish don't have fur, fish don't have legs, like, there's tons and tons of things. And I'd be more similar to a fish than I would be to a jellyfish. I'm more
Yeah.
similar to a jellyfish than I am to a tree. Like, and that's something you can measure just with comparative anatomy. That's something you can measure with genetics. And so that's not an evolutionary statement. And the trap we fall
Mhm.
into is thinking that those are evolutionary statements. And so we should not be afraid to affirm that there is relationship, right? There's similarity and dissimilarity, but that doesn't automatically mean that there is descent and that there's common ancestry, right? And that's the
Right.
trap we fall into. And so, I don't want to go into this saying, those aren't ear bones. Oh, that ear bones have nothing to do with jaw bones. Well,
Uh-huh.
clearly they do, right? Because our ear
Uh-huh.
bones are coming from our jaws during development. So there's some kind of link there, right?
Uh-huh.
And so this kind of caused me to, like, as I was working through this, I'm thinking, "Man, what do I do with this?" And there's a few different areas we kind of went after, right? And
Uh-huh.
so the first one is this idea of continuity discontinuity, right?
Yeah.
So the evolutionists are telling us it's this beautiful spectrum from something like Dimetrodon, right,
Mhm.
all the way to a mammal. Okay, that it's just this, like you said, this I gosh, I forgot the word. Oh, crown jewel, right? The crown jewel evolution, the best example, which I found out, as far as I can tell, is not an evolutionary invention. The crown jewel term that actually
Okay.
comes from the intelligent design community, which I
Oh,
didn't know
okay.
this, and I always assumed it was evolution who said it until I finally tracked it down. As far as I can trace it back, it came from the intelligent design movement. But um, is that really true? Right?
Mhm.
That I can draw a line from this to this, and it's just a beautiful spectrum, right? So that's the work I started doing with my students doing baraminology work. And what we found is no, absolutely not. It's totally punctuated by discontinuity, right? Pelycosaurs and therapsids are very different from each other, demonstratively different, right? And then within therapsids, you have all these different types, right? We already mentioned there's some that have beaks, there's some that look like this, right? And there's some that have very mammal-like faces. And it turns out, yeah, there's tons of different kinds of these things. So it's not shocking from a creationist perspective, but it's cool to see that, right? That we do see very clear statistical evidence for discontinuity, right? That I think we can
Mm.
interpret that way. So that's kind of number one, right? Number two to look at is, do the trends that they claim in the fossil record actually match, right? So they're saying you start more reptile-like and you become more mammal-like. Okay. So the thing is, if you zoom out, right, we have the geologic column right here, and you can see Dimetrodon down at the bottom, and then you can see some kind of therapsid in between, and then you can see one of these cynodonts near the top, and then a mammal. Yeah, for sure. You can see that trend, reptile to mammal, right? But then when you start zooming in, you realize this is actually really weird. Okay. So one example is there is rampant what we call homoplasy. Okay. So homology is when you say, like I told you, hey, this is a dentary and, I have a dentary, right?
Mhm.
We think it's the same bone. It's looks different, but it's, the same thing. I think I have a femur and an apatosaurus has a femur, right? I can say that.
Sure.
Okay. It's the same bone, might look different. Homoplasy is when you have these two very, very similar looking things. And, an evolutionist would say, well, I have a femur and apatosaurus has a femur because we share a common ancestor, right? As a creationist, I don't think that, but that's what they would say. With homoplasy, we're saying, well, this creature has this and this other creature has this, and they look like they should be related, but they're not. It's just, chance made it similar or something like that, right? So we've got three different groups at minimum that each independently develop a secondary palate on their own, just for fun. They just all mimic the mammalian condition, right? And when you look at that posture change, right, from being that reptile to being a mammal kind of thing, it turns out multiple groups are kind of doing this on their own, right? So we have separate finger bones. Okay. We have this pattern that goes 2, 3, 3, 3, 3. You've done this before. You played with your knuckles when you're a kid and you're like counting them. Reptiles are pretty different. So like my bearded dragon, it goes like 2, 3, 4, 5, 3, I think, or 4. I can't remember. Very, very different. And so his fingers are actually longer on the outside. It's kind of weird. And so there you can find therapsid fossils where it looks like they're changing into them, where some of the phalanges are like sticking to each other and they're little discs and things. But the mammalian condition, instead of it going reptile condition and then the mammalian condition shows up later and you have these in-between ones, what you actually find is, nope, like 5 or 6 different times the mammalian condition pops up on its own. And sometimes it shows up first and then the reptilian condition shows up. Sometimes there's like intermediate ones that are out of order. It's really weird, right? And so all of that put together, it's like it only makes this nice evolutionary sequence when you zoom out. But when you start getting the details, you realize something else is going on here. There was a paper that just came out, I think last week, where they were looking at the humerus, so the upper arm bone, in mammals and non-mammalian synapsids. And they compared it with reptiles and amphibians and all kinds of fun things. And they wanted to figure out, when did that postural change occur, right? Where reptiles move into mammal one. And so they found out, well, reptiles are in this little quadrant, and modern mammals are in this little quadrant of space, and then monotremes, like duckbill platypus and stuff, are over here. And they thought, oh, the synapsids are going to like link these two, or maybe go this way, like include the monotremes. They're just doing their own weird thing. Like, so reptiles would be confined in this little space. Non-mammalian synapsids, it takes up the whole board. Like, depending on your group, they're doing something completely different from group to group. And so this is just really, really weird. And so when I look at that, that doesn't scream out to me, oh, this is evolution. This is screaming out to me, there's something very different happening here. And that kind of takes us to the last thing, which is, how do you actually think through, for instance, that jaw to ear transition, right? What's going on there? And the first thing, like I said, is, hey, we affirm there's similarity. That's okay. Nothing we can, there's clearly a design plan at work here, right? Our ear bones are coming from our jaw tissue. But maybe we're looking at this backwards, right? We're expecting that the evolutionist is telling us, oh, your ontogeny, your growth, recapitulates your phylogeny. Okay. So the story is that your growth retells the story of your evolution, your evolutionary ancestry. Okay. But maybe instead, what you're seeing is that the ontogeny, your growth from an embryo to an adult, is giving us insight into the big design blueprint that God used for creatures, right? So maybe these cynodonts, they have the same growth trajectory, the same ontogenetic direction, right? How their embryos grow into adults, like mammals do. That starts off the same, right? And this is something that's been recognized long, long time back, right? So back in the 1800s, they were like, oh yeah, your embryo goes through a fish stage, and then you turn to an amphibian, then you turn to a reptile, and eventually become mammal, right? And Von Baer is like, that's nonsense. that's not true at all. You are never a fish at any point during your embryological development. Yes, good to know. What do? He says you start more similar and you become more different as you go, right? And so you can find this chart that Von Baer drew that looks like a cladogram. It looks like an evolutionary tree, but it's a chart showing how our development differs. So we develop most similarly to other mammals, right? And mammals develop more similar to each other than they do to reptiles and birds. And all of them share more development in common than they do with amphibians and fish, right? And that's not that shocking. We've all got to start off as a single cell. Whether you hatch from an egg or your live birth, you originally started as a single cell, right? And then that's going to look very similar. If I look at a frog single cell, zygote, and I look at a human zygote, unless I'm really trained, I don't want to look at that, right? Like it's a cell. And as it starts developing and multiplying, then I start seeing some differences. And the more similar two creatures are, the longer their development tends to be in common. And so I think what we're seeing here is that these cynodonts, they're developing along their pathway just like mammals are. And then God designed them to switch off at some point, to say, nope, your ear bones stay attached to your jaw. They stay jaw bones. They don't become your bones, right? Whereas the mammals, nope, they become your bones. And you think, well, what do you do with the creatures that have two jaw joints? We actually have modern creatures that have two jaw joints. They're called shrews. Now, their jaw joints are not built like the cynodont ones, the morganucodon ones, but it demonstrates that you can have, weird situations like that for functional reasons. It turns out it helps them have a more precise bite, we think. And they can, especially shrews, apparently they wear down their teeth really fast. And so having that mobile, like two jaw joint kind of thing allows them to process food as their teeth wear down, which is kind of weird. But okay, that's it shows me that this is not that maybe there are other reasons than just evolution for having two jaw joints.
Yeah.
So that's kind of like me trying to summarize everything I've been thinking about nonstop for like years.
Yeah. I mean, this is fascinating. There's an awful lot there to digest and to kind of wrap our heads around. But I think it's really interesting. I mean, if people don't go away with anything else, if they kind of understand that there's more to this story than first meets the eye.
Yes.
And there are kind of creationist ways to think about these things. And I love the way that you've kind of taken that idea of ontogeny recapitulating phylogeny, development, retracing our evolutionary ancestry, and actually kind of turn that idea on its head to kind of come up with a creationist sort of explanatory model that actually might help us to explain a whole load of stuff. So that is really, really interesting. And it's also interesting, that with the baraminology, you're finding that actually what looks maybe like a smooth evolutionary series is actually kind of chopped up into lots of component parts that don't actually share continuity with one another. One other thing I was just going to ask you about, and maybe you could touch on this, is abrupt appearance in the fossil record, because that's another thing that we see with some of these groups. Is that right?
Yes, and I totally left that off, so I'm glad that you brought that up. So, I mentioned there's the more reptile-like ones, the pelycosaurs, and then there's I guess I gotta use this guy, the more mammal-like ones, that are the therapsids, right? And so, pelycosaurs show up first in the fossil record, right? And they show up pretty abruptly in the Carboniferous. And there's a few, like 5 or 6 different families, and most of them disappear at the Carboniferous Permian transition, or into the Permian a little bit. I should say that, yeah, into the lower Permian. But by the time the therapsids appear, there's only like 1 or 2 of those left. The therapsids, there's like 6 different groups of them. Okay, of those 6, 5 of them show up simultaneously in the fossil record. Okay, so these 5 completely different groups, the ones with beaks, the ones with terrible heads, the ones with saber teeth, all these different ones just pop up, boom, 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 at the same time in the geologic record on multiple continents, right? So in the middle Permian deposits of China and South Africa and Russia and Brazil, they just pop into existence, all those different groups, and you're like, where did they come from? Like, this is really weird, right? And no matter the earliest therapsids they keep finding, they're recognizable as one of the groups, with maybe 1 or 2 exceptions, and they're very, very distinct. And so actually, it makes creating evolutionary trees for them very hard, for the big groups. Within the groups, yeah, you can do it. You can figure out how this dicynodont is related to that dicynodont. But how are the whole dicynodont group related to, one of these other ones, the Gorgonopsians or the Dinocephalians? That's really hard to do. And it turns out, there was a paper from 2009 where Kemp, one of the guys I mentioned earlier, is a big worker on this. He said, you know what? I think it was an actual polytomy. So if you study phylogenetic stuff, they talk about polytomies. And so it's when you have, you want your tree to always branch by 2, right? You always have this bifurcating branching tree, you'll see. And anytime you have a node and like dozens of branches come out from it, right? That's like, oh no, that's not good. That's not resolved. They'll say there's something wrong here. It's not supposed to do that. But technically, there's no reason it can't be, right? An evolutionary model. Like you could have 3 species come out of 1. You could have 10 species come out. There's no rule against that as far as we know. And he said, yeah, I think all of these different therapsid groups, except one, evolved rapidly. They just basically look like they suddenly appeared, because he says that's what the fossil record shows. And we can't ever resolve it because it happened so fast. That's what he said. And he said, you know what? It's actually a lot like the Cambrian explosion. And I'm like, oh, really? That's interesting. And that to me
Right.
says, yeah, this is not actual evolution taking place. These are not groups that are descended from a single common ancestor. These are, in fact, discontinuous from each other. And that would make sense.
Yeah. And certainly if we're thinking in terms of a flood model, and how we're kind of successively burying these different communities, as the flood waters kind of encroach onto the pre-flood world, abrupt appearance kind of makes sense, right? Because
Yes.
it's where the flood waters are just encroaching onto a particular ecosystem that has this diversity within it and burying it. And that's another whole area that we could, talk about. How does the flood relate to the formation of these fossil series? But I think we're kind of coming to the end because we're running out of time. But this is a huge topic, and I kind of feel like we've kind of raced through an enormous amount of stuff here. And I'm sure many of these concepts, these things that we've talked about, we will come back to them in future episodes. But that was fascinating. So just to conclude, I mean, where do you see this research going next? I mean, what have you kind of got planned, you and your students, on this
Yes.
particular topic?
So I'm gonna be. I've been writing a big monograph kind of thing, big technical book, on this, to be published with some kind of creationist publisher. I don't know. I don't know what's getting published. So really, really just tons of baremological analyses, all this kind of stuff, thinking through the ontogeny and diversification and all those kinds of things. And there's more of this coming out with some origins abstracts this year. And Kurt's been kind of jumping on some of this, Kurt Wise. But hopefully this book will get published sometime soon. We're still just making all the figures. It takes forever. And there's, hundreds and hundreds of figures of just baremological analyses. And what that means is no one's going to read it. So what you have to do then is create a version that people actually will read. So the plan is to also release one that will be for more the general public that would kind of explain these creatures and how we think about them as creationists and how these show the glory of God, right? Because regardless of whether we have answers for the evolutionary questions or whether they're never worrying, right? Even if we had never had this debate, these things would be worth investigating because they show the glory of God in very unique ways. We have a whole group of animals that's just gone, right? I mean, dinosaurs are cool, like we said, but these are things we can't even classify these things. And there's hundreds of species of them, right? And that is something really worth learning about then, right? And especially if there is this link that we're learning here between the way we grow and the big design plan that God used to make creatures, as well as their actual diversification. That's a really fascinating thing to investigate, and we need to start looking into that. And so I expect we'll start going in some of those directions. When I did all my baremological analyses, there were some groups that just no one's made good data sets for. So, that's going to have to be refined in the future. And as you brought up at the end, there's a ton of stuff when it comes to flood modeling and geologic record thinking and all that kind of stuff that we got to figure out. I went to South Africa as part of this. I got to go out there and see the fossils in the ground, which is really cool. And I visited
That's great.
this one spot where they've preserved the what do they call it, the Gunsfontein paleosurface or something like that. And it's basically a whole area full of footprints of these things. Just walking all over, and you can tell there was water. There's ripples on the ground. There's little invertebrate traces. And these guys are walking all over the place. You can see them slipping. You can see them, kind of like small ones, big ones, everybody. And you're thinking, when is this happening? How is this getting preserved? Like it's starting me thinking about what is going on during the flood. And so there's just so much that we don't know. And that can be discouraging, but I prefer to think of it as encouraging because, I remember one time I was working at a museum and this little kid came up to the window and he wanted a question, but he was scared to ask it. So his mom asked for him. And she said, he wants to be a paleontologist one day. And he's scared that all the dinosaurs are going to be found by the time he grows up. And he wants to know if that's true. And so I got to encourage him and say, no, because that's how science works. There is so much we do not know.
Yeah.
And so those of you who are listening to this, who have kids or you are younger and you're wanting to go into college and study science, like do it. There's so much to study, so much to learn.
Yeah. Well, that's been great, Matt. Thank you so much for kind of walking us through all of that. What started as a real kind of head scratcher for creationists, this huge evolutionary challenge that looked insuperable. It looked such an enormous problem. And actually, it turns out there are enormous opportunities for creationists to understand this and make some headway, and some really exciting things going on. And I hope people will take you up on your challenge there to get involved. Go and get trained at the Masters University. Go and study with Matt and work on these things. Why not? Thank you so much. That's brilliant. Well, that brings this episode to an end. Todd, as always, we don't know what's coming next. We don't know when this episode's going to fall in the schedule even. We haven't worked that out yet, but I'm sure it'll be just as much fun. So we will see you guys in another couple of weeks. We'll see you then.
See ya.
Thanks for listening to this episode of Let's Talk Creation. For more information, visit us at letstalkcreation.org, where you'll find an archive of past episodes and all our show notes. If you'd like to leave a comment or make a suggestion, you can find us on all the major social media platforms. Let's Talk Creation is brought to you in the U.S. by Core Academy of Science and in the U.K. by Biblical Creation Trust. As a listener-supported ministry, we are grateful for all of your financial support. Find out how you can make a contribution at our website, letstalkcreation.org. Also remember to like, subscribe, and share this episode with your friends. Thanks, and see you next time.